the last very speaker of Cosmos, I think introduce Ralf Kurvers, who's a senior research scientist at the Max Planck Institute for Human Development. He's going to present some work on information cascades in social learning and how decision making can be sometimes susceptible to these cascades. So give the floor away to Ralf.
Thank you very much, Charlie. Yeah, and also big thanks to Wataru and to Charlie for putting this together. It's I've been really enjoying this last couple of days, and I think all of us. So that yeah, thanks very much for the invitation and for putting this all together. It's really wonderful. So we're going to start out with like a 10-minute, just short experiment to kind of get you a little bit going. What kind of paradigms we are using here. Yeah, like Wataru already said, if you're sitting in the back, it might be that the signal of your clicker is not reaching here the laptop. So if you're really keen on getting your votes registered, and we'll show some results at the end, you can still move a little forward. So yeah, we're gonna first 10 minutes gonna play a game called the Shark Tuna game, and you have to imagine for the next 10 minutes that you are a tuna fish yourself, and you actually want to stay in the group to forage, but you should watch out because there will be sharks in the group. So you get to see these kind of images. And you see here a mix of tuna and sharks, cartoonish, obviously. And the decisions or the rule I would like you to follow is if you see 4 or less sharks, it's actually safe enough. You can stay in the group. However, in this case there are, for example, 4. However, if there are 5 or more sharks swimming in the group, then it's actually too dangerous, and you should escape. So how many are there here?
2, 6.
Okay, I wouldn't trust Wataru on this. All right, so there are 6 here. Yeah, so to make this even more fun, we're only going to show this for 2 seconds. And then we'll have 2 voting rounds. For the first voting, that's going to be your independent decision. So you won't see any social information, you just make a decision yourself. So there will be like a 5-second voting window, and it's quite important to vote within that period, not before or after, because then we're not picking it up. So you'll start hearing some music, and you see a countdown timer counting backwards. So only in this period you can vote. If you want to escape, so if you believe that there are 5 or more sharks, you can press the 1 on your machine. If you think there are 4 or less, and you want to stay, then you can press the 2 on your machine. You only need to press the number, not send or anything. And you can also like, maybe just to make sure we're receiving it, it's also okay to press 2 or 3 times the number. That's fine. Okay, so first you all make your independent decision, and then we'll do a second voting round for the same image without seeing it again. Now you get 12 seconds, and again the same decision rule. So if you want to escape, press 1. If you want to stay, press 2. However, what we'll do now is that when you make a decision, it will appear at the screen here. There's a little bit of a time lag, 1 to 2 seconds. But the idea here is, of course, that now you can, of course, decide how to dynamically adjust your timing of your decision. You cannot change. So if you make a very quick decision and maybe you see the whole group is going somewhere else, then you're stuck with that decision. And at the end of the round, you'll see the feedback. So what was the correct answer? And we'll do just 10 rounds in total. So this is going to be done in a breeze. Any questions? So let's have a very quick look at some of the results. So this is the accuracy of the first and the second voting that we just did. And I mean, obviously there's some, maybe some people missed more often the voting slot in voting 1, so you need to be careful here. But it looked like voting 2 is more accurate. Here you see the accuracy per round for individual and group voting. So you see in most rounds you see that voting 2 was more accurate than in voting 1, but also not in all rounds, as you can see. Here you can see on the back of your voting machine there's a number, and you can find yourself back here. You can keep it anonymous. So this is the first 15 individuals I will show for the first 15 voting machines. You see voting 1 is individual accuracy, voting 2 is social accuracy. And what is, for example, individual 13, 15, you see that they improved a lot with the social information. For example, individual 11 was individually extremely accurate. and did a little less well in the second voting, so maybe it was actually misled. And I mean, some values may be a little bit low because the reception was pretty bad. But maybe you can find yourself back here. If you see only one color, it means that your individual and social, or your voting 1 and voting 2 were actually of equal accuracy. So it's not jittered here. All right, so I wanted to start to kind of give you a little bit of an idea of kind of like the paradigms we've been using over the last years to study the cognitive mechanism underlying information cascades, and I hope to communicate a little bit how you can actually use computational modeling to actually make sense of what is going on here. I think I'm preaching to the choir here to say that to understand social and collective behavior, to really understand what is happening in these social systems, we would argue that kind of it really can help to actually have a close look at the cognitive processes of the individual agents in these systems. And that really kind of some of the main questions that we try to answer to get more insights here is to really understand, how do agents sample personal information, how do they extract information from their environment, how do they integrate this personal information with social information that they're receiving from others, and how are these processes dynamically unfold over time and contexts, and how can we use computational modeling to actually quantify such processes. And the kind of the approach that we decided to take is very much inspired on the framework of evidence accumulation models. The power of these models is that they not only predict what an individual will do, but also when they will do it. So they will predict response times. And as you can maybe have seen in that social phase, the response times are of course quite crucial here for what happens to social information, how is information cascading. So these kind of models, they kind of the main idea of how they think that the decision takes place is that over time an individual samples evidence from the environment. So for example, here you see a fictive line showing an individual first sampling some evidence in favor of escape, then in favor of stay, and finally more and more evidence towards in favor of escape, till the decision maker reaches a decision threshold or a decision boundary, and at that moment the decision maker will make a decision. And kind of the key cognitive parameters of this model, the key parameters are what is the start point of an individual, where does it start drifting? So here, for example, it starts drifting exactly in the middle, so equidistant of the both boundaries. Then how quickly can it actually extract evidence in favor of an option from the stimulus? So how quickly does it drift to either direction? And then the decision threshold. So how broad or how narrow are the decision boundaries set? For example, if you set very broad decision thresholds, you can imagine it takes you a long time to make a decision. Whereas if you operate with very narrow boundaries, you make relatively fast decisions. So this is also one way how individuals can modulate for example, their speed accuracy trade-offs. And these models have been extremely influential to account for a range of human choice behavior in many different domains and contexts. So from the formation of confidence judgments to the evolution of response bias to how influence attention shapes decision making. So this is already for many decades a very powerful cognitive model to predict and describe human choice behavior. Then my back then PhD and current postdoc, Alan Tump, he came up with the idea to actually extend this to the social domain. I mean, he could maybe even be in a much better position to give this talk. So Alan really developed all of these methods. So I think credit where credit is due, and I'm happy to defer any difficult questions to Alan as well. And what is quite cool is that actually nobody's really doing that. I think there were not many people in cognitive science who were actually thinking to actually apply these kind of methods to the social context. Whereas we at the same time know that, of course, timing is essential for dynamic social systems. So now all of a sudden you don't have a situation where a single individual is going through an evidence accumulation process and has to decide how to time their decision and what to choose. But you have multiple individuals at the same time starting to go through this process. And here you see, for example, five separate individuals. And what you, for example, see here is that they actually start with a different start point in this fictive example. So the green individual, for example, starts very close to the decision boundary of the escape threshold. So maybe that individual already collected some personal information in favor of escape. So it already formed the belief that this may be the true state of the world. Whereas the blue individual, for example, started much closer to the state boundary, and then some individuals more in the middle. And what Alan implemented is that as soon as one first individual makes a decision, in this case, the green individual, then all of a sudden, we don't only have kind of a drift that is influenced by your personal parameters, but you also get a social drift into the equation. And then finally, there was the social phase where individuals were free to time their decisions. And maybe I'm going to first ask, like, how did you decide when to make a decision in the social phase? What were your strategies? Okay, so you focus on one quadrant and then you multiply times 4 the number of sharks. Yeah, So what's very interesting is that what you see here is that you have very different strategies to search and to sample information from the environment. You can imagine that in a fish school where everyone has a very different heading, that a lot of these processes even amplify much more, right? Where you can only see a certain limited range. So kind of this distributed sensing that we believe that animal groups have, of course, plays a huge role in, and then of course, like what Ian Cousin also told about, like spatial positioning geometry comes really into play. But even if we standardize this and every individual has exactly the same tablet in front of them, we will still actually find that people use very different search strategies. So some will really scan left to right, others will try to look holistically at it, others take just one section. So it's certainly also, even for very standardized conditions, we will actually find this. All right, so let me show you kind of some of the behavioral results from a much larger sample, much larger groups. Kind of here you see the relationship between the confidence that people reported and the accuracy of their personal choice. And you see there's quite a nice relationship in the sense that if individuals report relatively high confidence, that also their personal accuracy is quite high, whereas if people respond the lowest confidence, 50%, their personal information is also actually of relatively low quality. If you then look at how this confidence in turn impacts the response time in the social phase, we also see quite a clear relationship. So individuals that were extremely confident, so reported 100% to us, they were also the ones that actually decided first in the social phase. So they were, if you like, the leaders in the social exchange. Whereas individuals with relatively low confidence, they were actually the ones holding back and perhaps waiting for social information. And did individuals, at least on a behavior level, seem to use social information? I think the answer is on a descriptive level seems to be yes, in the sense that if the majority size was favoring the correct option, which are the positive values, we see that individuals that did not decide yet, that they actually on average improve. So they really followed majorities. But they also followed majorities when the majority was actually incorrect. So the negative values here on the x-axis imply that majority was actually incorrect. And then you see that individuals actually start doing worse, but they still follow these majorities. But of course, what we were really after was not necessarily these behavioral descriptive levels, but really what cognitive mechanisms are actually underlying these processes. Can we actually estimate these parameters from a social diffusion model, and how do they then look like? So what Alan did, we built like several different models that we did comparative model comparison, as you heard yesterday in the tutorial. And you can, for example, think of, did my start point, for example, where I just started drifting at the start of the social phase, was this modulated by the personal information that I had and also the confidence that I have in that information? So you can imagine that your start point here is not neutral, but it actually depends on how much you believe to know about the environment. What can also happen is that in the social phase, that you could, for example, continues to still keep drifting towards the option you already believe is correct. So you could kind of reinforce the belief you already have. Another option is that you start drifting towards the correct option. We also see that often in experiments where individuals basically still sample from memory about the stimuli that they see, and over time then still continue to keep drifting towards the correct solution. So you really can see how many different mechanisms can come into play here. And then of course, what is the shape, for example, of the drift rate? And how broad or narrow are the thresholds? Then in this case, using the deviance information criterion to compare different model combinations, I'll present you kind of the parameters of the best fitting model. Let me first describe to you how personal information was integrated in that social phase. And there were two distinct ways of how people actually encoded their personal information in that second phase. And the first one is that they adjusted their start point as a function of the confidence that they had in their own information. So you see here in this graph where the colors are fitted lines for different group sizes, and all the gray lines are fitted on an individual. And what you see here is if on the x-axis, if somebody reports 100% confidence in the correct choice, independent if it's escape or stay, you see that they also start drifting more towards the boundary of the correct option. Again, independent is escape or stay. And of course, that makes intuitive sense, right? So if you are very confident that escape is the correct option, you probably don't want to start drifting exactly in the middle. You actually already are kind of like, if you like, biased in your information, and you also need much more evidence to actually be convinced of the other option, right? But you also see that this is symmetrical. You also see that this is happening if you have if you're very strongly convinced of the wrong information. So here on the x-axis, 0 means that you're 100% confident in the incorrect option or in the wrong option. And you see if that happens, then your start point is also relatively close to the decision boundary of the wrong option. Again, I think that makes intuitive sense. What is also what I find interesting when seeing these results is that the level of individual variation, right? So some individuals are relatively strong, S-shaped curves, meaning if they are confident, they will restart very close to the decision boundary. So they're very likely to make fast decisions. They're really hard to convince otherwise. Whereas other individuals, you see that their lines are actually much flatter, right? So even if they report 100% confidence, they are actually not really acting in the sense that they actually have, that they think they have a lot of evidence. So they're still, if you like, they still will on average wait relatively long with seeing what others think and may then also be influenced by that. So that's also, I think, one interesting thing is that you can really start to tease apart individual variation on a very, I think, detailed level. However, this was not the only way how personal information was integrated in that phase. Because what Ellen also managed to show is that individuals in the social phase still drift towards the option that they already initially chose. So if you already believed it was escape in your personal phase, then in the social phase you keep actually drifting towards the decision boundary of that choice. So in other words, you can really reinforce your beliefs that this is the correct option, which in some ways is interesting, right? Because you think, okay, there's no social information coming yet. That means everyone is still maybe in the same state of evidence, but that is actually not what is happening, right? So people are kind of more drifting more and more apart depending on that personal information that they have, right? So these are interesting processes that once you start thinking more about timing, actually, of course, start to really, really matter. If you then look at how social information was integrated, then you see here the different fitted curves for different group sizes, and again also for individuals. Of course, the individual variation is also more extreme here because we have these different group sizes. That explains part of the variance. What we see here is that kind of like the strength, to what extent you incorporate social information in your drift rate. So to what extent you actually start accumulating evidence for the option indicated by the majority, is mediated by the group size you're in. So a very small group size, which was actually, I think, around 3 individuals, so very, very small. You see that majority size of 1 and 2 have a much stronger effect than when you are in a larger group size. And for large group sizes, which I think was here around 25, we also see that like each additional member added on top of majority has always a little bit a lesser effect than the individual that was added before to the majority. So that also tells you something about the shape of these curves. That of course tells you something about how quickly social information can cascade through a population. That will of course depend heavily on these kind of shapes, right? So if you have really strong social drift rates, or small majorities already can very quickly convince others to follow suit. You'll of course see that you'll have much more consensus decision making and also much faster decision making. So both accuracy and speed will be mediated by these shapes. Looking at the choice thresholds, we saw that this was not a function of group size. So how much information you needed before making a decision was not mediated by the group size you were in. Again, what is noticeable here are also quite the strong individual differences in the choice threshold. So this really means that some individuals, they need relatively little evidence before making decisions, and others say they require a lot. I mean, you think of this as, of course, has ramifications once these kind of individuals get together. Yeah, then a very important part you heard yesterday, and I thought I wanted to mention it here as well to just re-emphasize, is can we then, with kind of the best model we identify, can we then actually recover some of the key, dynamics that we observed in our empirical system? Can we actually recover these patterns? Because if we cannot do that, then maybe our model is misspecified. So just to kind of stress that point again, that here you see relationship I showed you before between how much the majority size favoring the correct or incorrect option and whether individuals are expected to improve or not. And now the dashed curve here is the model prediction, simulating data based on the parameters that we estimated from the empirical data. And you see there's a really nice fit. And the same is true for this relationship between confidence and response time in the social phase. So top left, the empirical relationship, as we saw before, and bottom left, you see what is predicted by the model. So again, you see a very nice fit. And the same is true if we not take confidence as the measure of interest, but if an individual actually was correct or wrong in their personal information. We also see that kind of this key pattern that we found, namely that individuals that are correct, that they actually go on average faster than incorrect individuals. And yeah, again, I decided to include these slides yesterday, also after seeing the tutorials, because I also think it's a nice point to make that although this is a completely different modeling framework than what we've been hearing kind of in the tutorials, which was of course really using reinforcement learning as the case study. Here we although this is a associative diffusion model, is a very different modeling framework. A lot of the tools and techniques you learn when learning cognitive modeling can also then be applied to very different models, right? So a lot of the things in essence, or of course they sometimes have to be tweaked a little, but they are a lot of the steps in the cookbook that Charlie presented yesterday, can also exactly be applied here. So I think that's also an important lesson. And I also just showed it because I think the R values are so close to 1, so that yeah. So what we kind of see here is that we need to have like 2 conditions here that need to be met for what we call like beneficial self-organization. On the one hand, we need to have more accurate individuals have higher confidence. So individuals need to be aware of the quality of the information, personal information that they have. And second, these more confident individuals, they need to decide faster on average. That are kind of the 2 key ingredients that we need in order for these these information cascades to actually work in a beneficial way. And that also happened in most of the instances that we observed. Yeah, so it's kind of like, at least in this situation, what we tested, we really see that we have relatively fast deciding individuals that are both confident and accurate, and then we have individuals that are less accurate and less confident, and they wait longer, and they are getting socially influenced towards, on average, the correct decision, not on every instance, obviously. And what I think for me, when Ellen came with these ideas, and I'm still not really an expert in cognitive modeling. But I now also see the beauty and the richness that these kind of methods really kind of allow you to harvest. Because you now all of a sudden have this great theoretical framework that you can actually use to start making predictions and to really start understanding the dynamics. So for me, this is also really an eye-opener, and I now became also a big fan. So one question you may ask, and you may ask yourself as well, is like, how is leadership distributed in this task? And we've seen that before. This kind of debate between is it an unshared leadership where everyone or where a few individuals actually take the lead, or do we see much more shared leadership where it can be flexibly be decided, for example, on the quality of the personal information? And in terms of like thinking about this in terms of the DDM, this unshared leadership would be really expected if individuals consistently differ, if the variance in drift rate is between individuals, right? So some individuals are actually much better at extracting evidence than other individuals. Then we would expect really a high quality difference in how well individuals can play this task. And then we would actually believe that, okay, these are more the conditions where you would expect unshared leadership, right? Because you would expect them the high quality individuals to take over. Another scenario is would be much more in line with the idea of a shared leadership, is that the variance is not necessarily between individuals but the variance in drift rate is actually within individuals across trials, right? So individuals sometimes they manage to extract a lot of evidence in some trials, then they will act as leaders. In other trials, they will not manage to extract a lot of evidence because they maybe were looking at the wrong side of the image, and then they will more act as followers. And yeah, this is the beauty now, I think, with Alan developing this framework, you now can actually test which of these two situations is true or both. So here it was another experiment, group size of 10, quite a strong evidence for the second component, strong variation in drift rate. People are much quicker and decided to escape on average than decide to stay. And that's interesting, of course, because that has repercussions for the social system. At least that's what we believe, right? If you look at a group size 1, although there's an RT asymmetry, there's actually no overall bias to prefer choosing escape versus stay. So here you see for single individuals how often in an experiment with equal base rate with symmetrical payoffs, you see that they on average escape 50% of the time, more or less. And that's also what we usually would expect. However, if we now look at if we couple individuals in a group size of 10, and we do the same game we did here, we all of a sudden see that the average likelihood to escape is actually quite a bit higher than this 50%. And the reason for this is that these first decision makers are much more likely than a random individual to decide to escape, right? And this then cascades through the group, because these first deciding individuals have, of course, a relatively strong influence on how the rest of the group members will decide. So I think that's also just interesting to think about, just really simple things like small differences in how quickly decisions are being made in social systems. What can be the consequences of that? And it is, I believe, a very nice framework to capture such processes. Yeah, I mean, again, complementing this also with simulations, we see that we can actually only recover this kind of increased likelihood of choosing escape first, and then that it kind of like stays in the population or in the group. We can only capture that if we actually couple individuals socially. If we don't do that, if individuals make single decisions without social influence, we cannot recover that pattern that we empirically observe. So again, here you see the power of simulations to understand, yes, it is the social drift that is actually causing this effect. So one other way how to kind of like then think about such processes, how to bring this forward, is to use evolutionary algorithms to kind of let individuals evolve over time, to understand what would actually be optimal, cognitive parameters, if you like, under various ecologies or different environments. So here Alan ran a bunch of simulations where he varied the group size, and then also we started playing with the error cost asymmetry, so that making one error is much more costly than another error. Which, for example, in medical diagnostics, you typically really want to avoid a miss, whereas the false alarm is deemed less costly. And of course, for animals, being predated, of course, is a much higher error cost, much higher costly error. What's kind of interesting here is that what we observe is that individuals in very small group sizes, once the error cost asymmetry is relatively high, we observe that they start evolving a strong start point bias, and that makes sense, right? So that strong start point bias really helps you to avoid that costly error, right? So all things, if one error is very costly, the best thing you can do is just to evolve a start point bias that gets you very close to the decision threshold of that other option, so you are not actually it's a very low probability of making that costly error. What is interesting here is the more interesting thing is that actually in large groups, these start point biases actually are not evolving at all. And the reason why this is happening is because if everyone in a large group is actually very biased, then the group is making wrong decisions all the time. And because they're in a large group, they can actually avoid kind of making these errors by pooling their information. So they don't need to have actually to evolve such start point biases. So that is, I think that's a nice other way to think about how you can, what kind of methods you can use to then also make predictions about, let's say, different animal populations living in different ecologies, and then go and test some of these predictions. And then you can also, of course, play with where do you put incentives, or individuals evolving to maximize, their own individual level payoff. So really competitive environment, or are they trying to evolve parameters that maximize the collective benefit, the collective or the group outcome. And then, you also see interesting ranges where you see social dilemmas where, in theory, cooperative groups, would do better. Oh no, actually I don't have the accuracy here. But what you then, for example, see is that in these competitive groups, individuals start evolving larger start point biases on average. So they're actually everyone is trying to wait for the information of everyone else. And that, as a result, also leads to larger boundary separation. So everyone is like, okay, I'm going to wait. I need more evidence. And as a result, actually, individuals become less accurate in making decisions. So that's really one of these areas where you then find really a conflict between individual and collective incentives. Yes, another way, of course, we've been talking now about like fully connected groups where everyone is coupled to everyone. One of the things we also hope to make some headway is like what happens when you start we start introducing social structure. What happens then to the dynamics that are unfolding? And I think much of the social network literature is not using necessarily such a dynamic approach, but it's much more like a round-based approach. And of course, then they miss out maybe on when certain decisions are being made. So I think that could be potentially somewhat of a novelty here. An experiment we're going to start relatively soon. Well, actually, I'm going to skip this. Again, maybe some of these things, or we don't need to reiterate. But what I've been trying to kind of show here is that that there's a benefit of linking the cognitive process at the individual level to what happens at the collective level. That there's a lot of merit we can make here. And yeah, I think this actually kind of this general approach may also be applied in many different social contexts that you could think of. So I do feel that there's probably some merit of trying to think more in the dynamics of decision-making processes, rather than what we kind of often do is to tend to like really abstract them in round-based paradigms and not really kind of like let the natural timing decisions unfold or take them as object of study. And maybe in the last 5 minutes, just kind of shift gears a little bit, but just to give you a little bit of an overview of some things that we're currently doing, is that we're also trying to push this idea of individual cognition to understand collective foraging dynamics. So here we use, in cooperation with Pavel Manchung and David Messe, we use individual or agent-based simulations where these relatively naive agents are trying to search for resource patches. And then you can of course play also with how are they, for example, moving through a landscape, how strong are they socially attracted to other individuals, and from that we then try to generate predictions that we then test in human decision-making experiments. For example, this is a collaboration with Charlie, where we're trying to study what are actually the behavioral rules that individuals employ when looking for resources here in Minecraft. And then work led by Dominic Defner, was also here. We're trying to also kind of strip it even in some ways even more into the trade-offs we're actually interested in the sense that Minecraft is a beautiful platform, but of course it has also limitations in the sense that you can use only existing features that are at hand. So here we also kind of we build our own games in Unity. To also then really carefully manipulate environments to get even more at the heart of certain trade-offs that we are interested in. And yeah, again, of course, you can also then see here, you see some, I think Dominic called it when he first saw it, the snake pattern, playing snake on your phone. Then of course you can see that you can, you can see how rich the data is that you get from these kind of paradigms, where you can also think a lot about like where attention, for example, what is the role of attention? Where are you looking at? How does that shape your decision making? How did that shape in turn the resource distribution? Because of course, how you as an individual and collective act will determine how quickly patches, for example, disappear, etc., etc. And then finally, we're also trying to bring this really to the field, where we study ice fishers. So here you see the start of a competition that we organize. So these are 50 ice fishers, and they all go out for a couple of hours on the ice, and their goal is to maximize their catch. So here you see during the competition, so this is kind of what you often see. You see some individual drilling, others you see fishing, and you see they're relatively close together. So they're really concentrated in a patch. And then you also see a lot of individuals that are actually nowhere, right? So they could also go there. So these competition environments are like 2 by 2 kilometers. And then in the distance, you see another patch. And kind of the behaviors we then often see is that here you see a group of 3 individuals that are fishing at the same location. And you see then another individual that also decided to move there, to set up shop, start drilling and really use that social information. So you can imagine it's a very highly uncertain environment. So all of these individuals are tracked with GPS, so we can get relatively highly accurate or relatively accurate spatial solution. This is, I forgot to mention, his work led by Alex Tchaikovsky, who's also here. So you see, of course, there's a lot of things are happening here at the same time, where individuals are, where you see clusters forming, where more and more individuals are attracted to certain hotspots, till at some point the catch rates go down and individuals will disperse again. At the same time, you also see the depth curves of the lakes, and fish are, of course, not randomly distributed here. There are certain locations where fish are more likely than others. So it's an interesting, socio-ecological environment to study, decision making in the wild. What I think, so next to GPS tracking these individuals, they all have a head camera that I think will start in a second. No, there we go. So every individual actually has a head camera here, which allows us to, in detail quantify all the behavioral states they could possibly be in. So for example, here you see an individual moving through the landscape. Here it's clearing some ice, some moving away some snow to start drilling. Here you see drilling a hole. And you see the individual fishing, and we also, so with this we can actually also record every single catch in the system. We sometimes have a camera that fails, but by and large these things are working extremely well. So from every agent, we actually can get continuous information about how they are doing, and of course not only how they are doing, but also how their social environment are doing, individuals close by or maybe far away, to see how that individual level information combined with what you see around you and what you may know about the ecology shapes your decision making. And then finally, we also have parallel systems on robotics, where we can try to see, can we actually get at similar processes in terms of how agents coordinate, but using relatively simple embodied systems. So these individuals, they have like light sensors, so they are searching for patches of light, and they can communicate with each other with via infrared. And this is certainly not my work, not my expertise. But this is within Science of Intelligence Access Cluster in Berlin, where there's a very tight integration between people working on empirical systems and people working on synthetic systems. Yeah, so kind of with that, I'd like to finish, where we kind of really try to understand like how do collectives like balance, personal social information use to achieve high either individual or collective performance. How do they learn about which strategies actually to use? So how can they dynamically actually adjust their strategies based on information they're receiving? And how do these things vary with the size and the cognitive complexity? For example, sensory constraints. How far can you look of collectives, and also the role of environment? And I think it's still, I think, very much an open goal, an open question to what extent we can actually like get these like cognitive computational models that we've been discussing in the last days. Actually, how we can actually get them to work in these kind of environments, because of course usually we of course strip down the very complex and rich decision-making settings in real life to kind of the things we're actually interested in. So I think that's also not to me fully clear yet how much of these methods we can actually employ here, but that's at least I think a nice challenge. Yeah, so with that, I would certainly want to emphasize that again, that this first part was really Alan's work, supported by Tim Pleskaus, Max Wolf, and Pavel Manchuk, and then a bunch of other collaborators for the second part of the talk. Yeah, thank you very much for your attention.